Hi, my name is Rohan Rathod, and today I will be presenting my findings on the Physics 2211 Lab 1. This presentation will cover an introduction to the lab, key concepts that are applicable to the lab, a video of the motion that I captured, the data I got from the tracker, the computational model, comparison of both models, and then finally a conclusion. This lab is aimed at analyzing the motion of an object moving in one dimension at a constant velocity and developing a computational model based on that analysis. Three important assumptions for this lab are that the object is moving in one dimension, it has zero acceleration, and that the computational model has no friction and no drag due to air. The key physics concepts related to this lab are the position update and velocity update, and also Newton's first and second laws. The position update formula says that the final position over time interval can be obtained by adding velocity average times the delta t to the initial position. And then the final velocity can be obtained by adding the initial velocity to F net, which is a net force over the mass times the delta t, or the change in time. And according to Newton's first law, or second law, F equals ma, which means force equals mass times acceleration. Because of this, the velocity update formula is essentially just saying that the initial velocity plus acceleration times delta t equals the final velocity. And then Newton's first law says that an object in motion stays in motion unless acted upon by an outside force. This is the assumption we will have concerning the object in the coming video, because there's no net force acting on the object, so it should continue moving at a constant velocity. And here is a free body diagram of the object. We have the force of gravity, weight acting downwards, and then normal force counteracting it upwards, and then we have force applied towards the left. In this case, the object is the system and everything else is the surroundings. And here's a video of the motion I captured. The tracker data yields this graph where the vertical axis is the displacement, or the position, and the horizontal axis is time. To use in my computational model, I was interested in the initial velocity at the start, and to find this, I used a slope formula and picked 2 points on this line that were very close to 0, 0. And this yielded negative 0.77, which means that the initial velocity of the object is negative 0.77. Here's the computational model used to predict the motion of the object. I started by setting the initial position to 0 and the initial vector for velocity to negative 0.776, because that is what I found using tracker in the slope formula. The time starts at 0 and increments by 0.01 seconds, and the while loop will run for 1.2 seconds because the tracker shows motion stopping at 1.2 seconds. The velocity is defined using the velocity update formula, and the ball dot position is defined using the position update formula. Fnet in this case is 0 because the object is moving at constant velocity. This means that in the velocity update formula, the velocity will stay the same throughout the whole experiment. The graphs from the computational model show a constant velocity and a steadily decreasing position. Here's a graph of the tracker and computational model data. The two models start out very close but start to diverge as time progresses. The computational model reaches a farther distance at 1.2 seconds than the tracker does. And this is due to two things: the existence of frictional force in tracker and the lack thereof in the computational model, because I ignore friction in the computation, but in real life, in real motion, there is friction. And of course, human error in measurement and calibration can affect this. To conclude, I want to answer some post-processing questions. For one, what if I had reversed the axes in my tracker? If I had done so, the comparison of the models would show a large divergence in the motion of the object. The flipped tracker data would display motion in the first quadrant of the Cartesian coordinate system, while the computational model would show motion in the fourth quadrant. Although the distance traveled would be the same, displacement would differ. And is it possible to say how many forces were added to create the net force of zero? This is possible using the free body diagram in the earlier slide. We have gravity acting downwards and normal force perfectly counteracting that upwards to create a net force of zero on the object.